The Address Resolution Protocol, or ARP, is the mechanism by which the network layer can discover the link address associated with the network address it's directly connected to. Put another way, it's how a device gets an answer to the question, I have an IP packet whose next hop is this address. What link address should I send it to? ARP is needed because each protocol layer has its own names and addresses. An IP address is a network level address. It describes a host, a unique destination at the network layer. A link address, in contrast, describes a particular network card, a unique device that sends and receives link layer frames. Ethernet, for example, has 48-bit addresses. Whenever you buy an Ethernet card, it's been pre-configured with a unique Ethernet address. So while an IP address says this host, an Ethernet address says this Ethernet card. 48-bit Ethernet addresses are usually written as a colon-delimited set of 6 octets in hexadecimal, such as 0:13:72:4C: D9:6A, as in A in this example, or 999,999 as in the destination B. One thing that can be confusing is that while these link layer and network layer addresses are completely decoupled with respect to the protocol layers, in terms of assignment and management, they might not be. For example, it's very common for a single host to have multiple IP addresses, one for each of its interfaces. It needs to because of the concept of a net mask. For example, look at this hypothetical setup with A, B, and a gateway. The gateway in the middle has a single IP address, 192.168.0.1. It has 2 network cards, one connecting it to destination 171.43.22.5, one connecting it to the source on the left, 192.168.0.5. Now the gateway's address, 192.168.0.1, can really only be in one of these networks. The network on the left, the source network A. The net mask needed for 192.168.0.1 to be in the same network as 171.43.22.5 is 128.0.0.0, or just one bit of net mask. It can't be that all IP addresses whose first bit is 1 are in the same network as 171.43.22.5. 192.168.0.5, for example, needs to be reached through the gateway. So instead, we often see setups like this, where the gateway or router has multiple interfaces, each with their own link layer address to identify the card, and also each with their own network layer address to identify the host within the network that that card is a part of. For the gateway, the left interface has IP address 192.168.0.1, while the right interface has IP address 171.43.22.8. The fact that link layer and network layer addresses are decoupled logically, but coupled in practice, is in some ways a historical artifact. When the internet started, there were many link layers, and it wanted to be able to run on top of all of them. These link layers weren't suddenly going to start using IP addresses instead of their own addressing scheme. Furthermore, there turns out to be a bunch of situations where having a separate link layer address is very valuable. For example, when I register a computer with Stanford's network, I register its link layer address, the address of the network card. So what does this mean in practice? Let's say node A on the left wants to send a packet to node B on the right. It's going to generate an IP packet with source address 192.168.0.5 and destination address 171.43.22.5. Node A checks whether the destination address is in the same network. The net mask tells it that the destination address is in a different network, 255.255.255. This means node A needs to send the packet through the gateway or 192.168.0.1. To do this, it sends a packet whose network layer destination is 171.43.22.5, but whose link layer destination is the link layer address of the gateway. So the packet has a network layer destination 171.43.22.5 and a link layer destination 018E7F3CE1A. The network layer source is 192.168.0.5 and the link layer source is 013.72.4C D9.6A. So we have an IP packet from A to B encapsulated inside a link layer frame from A to the left gateway interface. When the packet reaches the gateway looks up the next hop, decides it's node B, and puts the IP packet inside a link layer frame to B. So the second IP packet from A to B is inside a link layer frame from the right gateway interface to B. So here we get to the problem ARP solves. My client knows it needs to send a packet through the gateway that has IP address 192.168.0.1. To do so, however, it needs to have the link layer address associated with 192.168.0.1. How does it get this address? We somehow need to be able to map a layer 3 network layer address to its corresponding layer 2 link layer address. We do this with a protocol called ARP, or the Address Resolution Protocol. ARP is a simple request-reply protocol. Every node keeps a cache of mappings from IP addresses on its network to link layer addresses. If a node needs to send a packet to an IP address it doesn't have a mapping for, it sends a request. Who has network address X? The node that has that network address responds saying, I have network address X. The response includes the link layer address. On receiving the response, the requester can generate the mapping and send the packet. So that every node hears the request, a node sends a request to a link layer broadcast address. Every node in the network will hear the packet. Furthermore, ARP is structured so that it contains redundant data. The request contains the network and link layer addresses of the requester. That way, when nodes hear a request, since it's a broadcast, they can insert or refresh a mapping in their cache. Nodes only respond to requests for themselves. This means, assuming nobody is generating packets incorrectly, the only way you can generate a mapping for another node is in response to a packet that node sends. So if another node crashes or disconnects, its state will inevitably leave the network when all the cache mappings expire. This makes debugging and troubleshooting ARP much easier. So how long do these dynamically discovered mappings last? It depends on the device. Some versions of Mac OS X, for example, keep them for around 20 minutes, while some Cisco devices use timeouts of 4 hours. The assumption is that these mappings do not change very frequently. This is what an ARP packet actually looks like. It has 10 fields. The hardware field states what link layer this request or response is for. The protocol field states what network protocol this request or response is for. The length fields specify how many bytes long the link layer network layer addresses are. The opcode specifies whether the packet is a request or response. The 4 address fields are for requesting and specifying the mappings. Remember, all of these fields are stored in network order, or big endian. So if you have an opcode of 15, it will be stored as 0x000f in the opcode field. So let's say our client wants to send a packet to the broader internet through its gateway, but it doesn't have the gateway's Ethernet address. The ARP request will specify that the hardware is Ethernet, which is value 1, the protocol is IP, which is value 0x0800, the hardware address length is 6, and the protocol length is 4. The opcode will be request, whose value is 1. The ARP source hardware field will be the requester's Ethernet address, 68A86005828522. The source protocol field is the requester's IP address, 192.168.0.5. The destination hardware address can be set to anything. It's what the packet is trying to discover. The destination protocol address is the address the client is trying to find a mapping for, 192.168.0.1. The client sends this frame on the Ethernet. Every node in the network receives it and refreshes the mapping between the sender's link layer address, 68A860058522, and its network layer address, 192.168.0.5, or it inserts a mapping if it doesn't already have one. The client will generate an ARP request whose link layer source address is its address, 68A860058222. The destination link layer address is the broadcast address, FF, all ones. The gateway sees that the request is for its IP address and so generates a reply. Like the request, the ARP reply will specify that the hardware is Ethernet, which is value 1, the protocol is IP, which is value 0x0800, the hardware address's length is 6, and the protocol length is 4. The opcode will be reply, whose value is 2. The ARP source hardware field will be the replier's Ethernet address, 018E7F3CEA1A. The source protocol field is the answer, 192.168.0.1. The destination hardware address is the source address of the request, 68A860058522. The destination protocol address is the source protocol address of the request, 192.168.0.5. It's an open question what link layer address you send the response to. The original ARP specification stated that the replier should send it to the requester's link layer address, so unicast. It's common today to broadcast it, however, as doing so can more aggressively replace cache entries if the mapping needs to change. Nodes also can send what are called gratuitous ARP packets, requesting non-existent mappings in order to advertise themselves on the network. So we've seen how, in order to route packets, one needs to be able to map network layer addresses to link layer addresses. The Address Resolution Protocol, or ARP, provides this service through a simple request-reply exchange. If a node needs to send a packet to or through an IP address whose link layer address it does not have, it requests the address through ARP.